and today's video is going to talk about stress due to torsion. All right, so let's start by going over an outline of today's video. We're going to define torsion, and then we're going to go over the torsion formula. We're going to talk about the angle of twist, go over an example problem, and then I'm going to leave you with a practice problem for you to try on your own. So what exactly is torsion, right? So torsion, best way to define it, is this twisting motion. And what causes this twisting motion? Something called a torque, okay? This is similar to a moment, but it's not exactly the same. A moment causes bending around the z-axis of our member, okay? But now we're talking about some type of twisting or turning around the longitudinal axis of the member or the x-axis of the member, right? So moment is rotation about the z-axis. When we're talking about torsion, we're talking about this twisting or rotation about the x-axis, okay? You can kind of take your arm here, and if you were to apply this twisting motion to your arm, right, you're applying kind of a torque. Twisting, that is torsion. You're applying this torsion to your arm, okay? So you can kind of think of your arm as a beam, right? So now that we know a little bit about, or a refresher on what torsion and torque is or are, we're going to discuss the torsion formula, okay? So we're not going to go into the full derivation today. We're going to kind of skip over a few parts, but I do want to refresh your memory on kind of those important pieces. So let's say we have this long, slender, circular element, okay? And draw this to the best of my ability here. It's not, hopefully it's not the best. Okay, let's see. And a circular face there, okay? And we'll say this is kind of fixed to the wall. This is the z-axis here, okay? And this is that x-axis that we're twisting about, okay? So we're applying this torque about this x-axis. I'm going to call this torque T, okay? And what happens here, and the y-axis is kind of going in. It's kind of hard to see, but I will try to draw it this way. Y-axis is going in that way, okay? What's happening here as we twist this element is it's kind of, if this is the center point, it's deforming and it kind of ends up, right, doesn't have any movement at the fixed support. We end up getting this angle that develops as we twist and turn. This little angle here develops, okay? And we call this angle the angle of twist, which we denote with the Greek letter phi. Angle of twist, okay? And T, just so we can define all of these, T is equal to the torque that's applied around the x-axis. And this is basically the moment that causes twisting, okay? This angle here, this angle that we've defined, the angle of twist here, phi, it decreases as you get closer to the fixed support, right? There's less deformation as you get closer to the fixed support, okay? So let's continue here, okay? So what we want to define is we want to remember the formula that relates shear stress to torque. So what we're asking ourselves is when we apply torque to a system, what is the shear stress that develops from that torque, okay? So I'm going to go ahead, I'm going to write the formula down for you here without having to go too much into that derivation. We have tau max, which is the shear stress max, is equal to Tc over J. And then tau at any point on the system is equal to T rho over J. So hopefully these two formulas should ring a bell. Okay. And let's go ahead and define what these values are, okay? So what we have is here, I'm going to start with T. That is equal to my torque, right? Tau is the shear stress. Okay. What is J? Remember, J is our polar moment of inertia. Okay, polar moment of inertia. And then we have C, right? Come down here. C is basically equal to our radius. It's just another way of denoting R, our radius. What radius are we talking about? The radius of this circular bar. Okay. And what is rho? Rho is just any arbitrary distance that I want the stress at. Okay. Rho is an arbitrary distance. So I'm going to draw a circle, face of that element like this. Okay. And let's say we have this line in the center here, right? And we have some twisting that takes place. Okay, so we have some angle phi for the twisting, and we want to know what the shear stress is from the center of that element to this point rho. Okay, where would tau max occur? That would occur all the way at C, the radius of the element, or R, call it what you like. Okay, for an example where we can apply the formula that we just refreshed our memory on to solve for the shear stress due to the applied torque. Okay, so I'm going to draw a solid circular shaft with a uniform cross section. So I'm going to start right here. Okay. Let's say we have a fixed to the wall system here at point E. I'm going to call this point A, and I'm going to define some points in between here. So I'm going to define a point B, C, and D. Okay. Now, we're going to apply some torques to this system. So I have a torque here. I'm going to say that this torque is 68 Newton meters. I'm going to say that this torque here at point B is 20 Newton meters. Torque at C is 49 Newton meters. And the torque at D is 35 Newton meters. Okay. So now what I'm going to do is I am going to ask 3 questions here. Let's, 1, calculate the internal torque. Number 2, let's draw the internal torque diagram. And number 3, let's find the max shear stress. Okay, so let's go ahead and calculate the internal torque. I'm going to make this a little, add a page here. Okay, so let's start here. I'm actually going to take this from this 3D image to a 2D image and make it a little bit easier to draw out. Okay. And when we take it from the 3D to the 2D, we can draw the torque as a double arrow, like this. Okay, so we can draw it as a double arrow. This is point A, point B, point C, point D, and we have 68, 20, 49, and 35, and this is all in Newton meters. Okay. And I'm going to section this off into section 1, section 2, section 3, and section 4. So I need to figure out what's happening in all of those sections. I need to find T between A and B, T between B and C, T between C and D, and T between D and E. Okay. Now, let's start with part 1 to find that internal torque. How do we do that? We make cuts. So I'm going to do 1 cut for you. I'm going to show you how this is done, and I'm going to leave you to do the rest on your own after I show you this one. So we'd have a TAB here. This is point A. We have the torque at point A, which is 68 Newton meters. And now we get T, just by equilibrium, TAB has to be 68 Newton meters, right? Okay, that's one. I said I'm going to do one, but I'm actually going to do two for you. So, next cut is going to be between 0.2, right? So we still have this is probably easier if I just copy and paste it from my original. Let's come here. 0.2 will be here. There we go. So I have this internal torque here, which is the torque between point B and C. So if I sum everything up, I end up getting TBC is 48 Newton meters. Okay. If I keep going and making these cuts, cut 3, cut 4, I end up getting TCD is 97 Newton meters, and TDE is equal to 132 Newton meters. Okay. And now I can move on to number 2, and I can draw that internal torque diagram. So I'm going to come back here. I'm going to copy and paste this image. And I'm going to go ahead and draw my axes for this torque diagram. And this here is the torque in Newton meters. And this is my x-axis in meters. From 1 to 2, let me draw some reference lines on this. Okay. Now, from 1 to 2, I'm at 68. Then I drop by that 20. So that takes me to 48. Then I jump up by 49, which takes me to 97. Then up by 35, takes me to 132. And back down, everything checks out. And I know, what is my max T here? My max T is 132. Right? So now I am ready for almost calculating this shear. I'm going to come back up here. Right? I want tau max. TC over J. Now, J is the polar moment of inertia. So, for a solid circular shaft, it's going to be pi over 2, c to the 4th. What is c? That is the radius. What is the radius of this shaft? We're going to use 50 millimeters for the diameter. So I'll put that here, diameter, 50 millimeters. That would have been given in the problem, which means that my J here, I'm going to say pi over 2 times 25 to the 4th, because I'm dividing by 2. I get 613,592.4 millimeters to the 4th. That is my J value. When I plug everything in, tau max is equal to 132 Newton per meter times 125 millimeters for my radius. I'm going to convert everything 1,000 millimeters per meter. So I can't keep it in millimeters and meters up there. And then 613,592.4 millimeters to the 4th. I end up getting 5.378 newtons per millimeter squared. Or I can just say 5.378 megapascals. And that is my final answer. So now that we've tried that problem together, try this practice problem on your own.